Hello everyone, and welcome to some more remote learning. In this example video today, we're going to get into trigonometric substitutions. So how trig subs work is essentially we're going to be converting sums and differences of squares. For example, a squared minus x squared, a squared plus x squared, or x squared minus a squared. We're going to change those into products of squares so that we can simplify within those exponents by using trig identities. And for our purposes, there are these three main trig substitutions. We're either going to be substituting in that x is equal to a sine of theta, x is equal to a tangent of theta, or x is equal to a secant of theta. From there, we'll set up our triangles based on this relationship. So just remember those three, it's either going to be sine, tangent, or secant that's multiplied by a to give us what we're plugging in for x. So let's take a look at sine at the start. If we have that x is equal to a sine of theta, and this red arc indicates theta, let's fill in our triangle based on this relationship. So if x equals a sine of theta, if I divide both sides by a, that means x over a equals sine of theta, right? Which we know that sine is going to be opposite over hypotenuse. So with this relationship, I know that opposite my angle theta is going to be x, and my hypotenuse is going to be a. Well, from there, I can use the Pythagorean theorem because this is indeed a right triangle. I know that my sides squared and then summed together equals my hypotenuse squared. So I'm going to reverse that because I know my hypotenuse in a side. I know that this other side is going to equal the square root of my hypotenuse squared minus the known side squared. So a squared minus x squared. And that's that side there. So with that being said, when we have an a squared minus x squared, the relationship we're going to be using is that x equals a sine of theta. And you will see in the next two, we're going to get some relationship of a squared plus x squared, the sum of those, and then the other one will be x squared minus a squared. But a squared minus x squared, we're using this relationship that x is equal to a sine of theta. And why we're making those changes is because you're going to be able to see that when we plug in that x equals a sine of theta, we're going to be able to use one of our identities to simplify to make it a product as opposed to having subtraction or addition in between. So a squared minus x squared, if x equals a sine of theta, that means a squared minus a sine of theta squared is this relationship. So you see, all I did was plug in a sine of theta for x. We can easily simplify this down. A squared minus, well, a sine of theta squared, I have a product, so I can distribute my exponent to both a and my sine function. So I'm going to distribute that in to get a squared sine squared of theta. Now, what do you see that I have in both of my terms? I have an a squared. So why don't we just go ahead and pull that out in front? If we pull out that a squared, then I'll be left with 1, because pulling out a squared from a squared leaves us with 1, minus just a sine squared theta. This should look familiar. 1 minus sine squared theta equals what? Think back to our identities, or actually, I think I put it on the paper. If you scroll down to the second page, looking at our Pythagorean identities, we have this relationship here, except we have 1 minus that sine squared theta because we subtracted it from both sides to give us cosine squared theta. So 1 minus sine squared theta equals that cosine squared theta. So this is equivalent to a squared times cosine squared theta. So that is what my a squared minus x squared is when I plug in an x of a sine of theta. Now think about why we did this. It's in order to simplify a problem. So we switched our variable from x's to thetas by making that substitution. And why this is helpful is, could you imagine if we had a square root around this? there'd be no way to simplify this square root. But if we have a square root around this, where we have a product, then we can easily apply that square root or that exponent of 1/2 to each of our terms. So if this was, as opposed to the square root, let's say that this entire chunk was raised to the 3/2. Well, again, simplifying when we have subtraction or addition is a no-go. But if there's multiplication in between, well, when this is raised to the 3/2, we just take that exponent and apply it to each of our terms. So that's why this trig substitution works out, is because it allows us to simplify our problem down. And another helpful hint is if you don't remember that the three potential options are a sine of theta, a tangent of theta, or a secant of theta, if we think about a squared minus x squared, if we plug in some trig function for x, where it's a times that trig function, we're going to be able to pull out that a squared and get 1 minus our trig function squared. 1 minus a trig function squared is going to represent 1 minus sine squared. That's that identity we get. And when I go through the next few triangles, you're going to see other identities that will appear to make this easier and more intuitive so you don't have to think about memorizing something. Or another way to help me remember what my potential x substitutions could be, I think about those trig functions will give me positive derivatives. So like, for example, sine gives me a positive cosine, whereas if I tried using cosine, I'd get a negative sine. Or secant gives me a positive secant tangent, where if I did cosecant, I'd get a negative cosecant cotangent for the derivative. And then lastly, that tangent gives me a positive secant squared, whereas if I put in a cotangent, I'd get a negative cosecant squared. So that's another helpful hint for remembering what three substitutions that we're going to be using throughout these problems. And one more quick tip that will help you with the bookkeeping of the problem is we're going to solve for dx, because when we make that substitution, think about u substitution. We plug in u for x and we try to figure out a dx that's in terms of du. Same concept for this. We're going to solve for x and dx and plug those in for each. So the derivative in this case, dx, is going to be a cosine of theta and that d theta. That's what we wind up plugging into our integral when we simplify. So again, x equals a sine of theta. We plug that in when we have a squared minus x squared. Let's look at x equals a tangent of theta. Well, how we set up our triangle, we're going to have x over a equaling tangent of theta. Because once we figure out what that trig function is, tangent is opposite over adjacent. If theta is that red arc, opposite is x, adjacent is a, and then our hypotenuse is going to be the square root of x squared plus a squared, or a squared plus x squared. It's a sum, so it doesn't matter the order that we sum. So, with that being said, we're going to use this substitution when we have an a squared plus an x squared in our problem. So let's look at how that identity factors in. If we have a squared plus x squared, remember, our x that we're plugging in is a tangent of theta. So this becomes a squared plus a tangent of theta squared, which I'm going to simplify down like I did before because I can distribute that exponent because it's a product. So I'll have a squared plus a squared times the tangent of theta squared. Pulling out that common factor of a squared, I'll get 1 plus tangent squared theta. And here is where we can use another one of our identities. That identity is the relationship between tangent squared and secant squared. So if we scroll down, we're looking at this identity here when you go to that second page where I put that nice formula box. Tangent squared plus 1 equals secant squared of theta. So this is really a squared times secant squared theta. And just like before, think about if we had this raised to the 1/2, to the 5/2, to the 1/3, etc. We would not be able to simplify it down with that addition, but once it's a product, we totally can simplify it down. Let's scroll up and find dx. dx is equal to a secant squared theta d theta. So what I'm doing in each of these columns is just a little bit of bookkeeping that's going to help you when you go to actually start solving these trig substitution problems. So as far as my bookkeeping goes, I find my x dx so that I know what I'm substituting in. I set up my triangle so that I can go back to that after I integrate, which you'll see happen in the examples. And then I also figure out what that sum or difference of the square is, simplified down using that identity, because it's going to be easier to do this outside of the integral and plug that in for a squared plus x squared than it will be to do that within the integral. However, this step is completely optional. You can feel free to do this within the integral itself. It just requires a bit more writing. And again, we'll get practice on this in our examples. So if I'm saying that x is equal to a secant of theta, that means that dx is equal to a secant theta tangent theta d theta. There's my derivative. Now let's set up our triangle. Well, this relationship says that x over a equals the secant of theta. But what is the secant of theta? Secant of theta is 1 over cosine. So if secant of theta is 1 over cosine, if I flip this fraction, I know that a over x is equal to cosine of theta. So let's set up our triangle. If that arc is theta, cosine is adjacent over hypotenuse. So now my x is my hypotenuse, my adjacent side is a. That means that the other side is going to be x squared minus a squared. So when we have x squared minus a squared, we use the relationship that x is equal to a secant of theta. Scrolling down, if x equals a secant of theta, that means that a secant of theta squared minus a squared is equal to x squared minus a squared. Again, bringing that exponent in, we get a squared secant of theta, that quantity squared, minus a squared. Pulling out that a squared, we get secant squared theta minus 1. What is this? Well, we know that tangent squared theta plus 1 equals secant squared theta. So secant squared theta minus 1, using that identity that we used for that tangent, we're going to get that secant squared theta minus 1 is tangent squared theta. So this is equal to a squared tangent of theta, that quantity squared. So whenever we have an x squared minus a squared in our problem, we know we can get to some product. That way we can apply those exponents. So again, x equals a sine of theta, we use that for a squared minus x squared. X equals a tangent of theta, we use that for a squared plus x squared, or x squared plus a squared. And for x equals a secant of theta, we're going to use that for x squared minus a squared. So there we go. We covered those 3 sums and differences that I mentioned at the beginning of this worksheet. So let's move on to the steps behind actually going through with an example problem. How do we integrate? So our step 1 is to identify the type of substitution needed and complete the necessary bookkeeping. So we're going to do exactly what we did up above, figure out whether we have an a squared minus x squared, an a squared plus x squared, or an x squared minus a squared, use the correct substitution for that, and then do the bookkeeping like above. Now what we haven't talked about is that next step, we're going to change that original integral. So if it was in terms of x, we're now going to make it in terms of theta. And I made a note that we don't want to forget plugging in for dx as well. So not only are we plugging in what x is, we have to plug in what dx is. And if we did the proper bookkeeping, there should be a note on our paper for doing that step. Next, once we do that, we simplify and integrate with respect to theta. Why we're plugging in theta as opposed to working with x is because using theta will simplify our problem and make it easy to integrate. So once you plug in those things in terms of theta, simplify and integrate. Then once you integrate, just like a u sub, we convert back to that original unless we have bounds that are easy to substitute in. And for this case, when we go back to that original variable, we are going to use that triangle when necessary. That triangle, think of it like a map. we use it to help us figure out that substitution that's needed, but then we also need it to go back to our original variable. So let's jump into some practice problems to really help solidify these steps. So in example 1, I have the integral of x squared over the square root of 25 minus x squared dx. That sum, or difference of square, is going to be this 25 minus x squared. That's my a squared minus my x squared. So if 25 minus x squared is my a squared minus x squared, what's my a? Well, if I have 25 minus x squared as my a squared minus x squared, that's telling me the square root of 25 is 5, so this is 5 squared minus x squared. Knowing that my a is 5 and I have a squared minus x squared, what's that step 1? Let's refer back to it. We need to identify this type of substitution needed and complete the necessary bookkeeping. If I have a squared minus x squared, that's going to be that x is equal to a sine of theta. And if you didn't know that relationship, refer back to the beginning of the worksheet or think about those different triangles we can create. But a squared minus x squared, we're going to use the fact that x equals a sine of theta. And you can also think quickly about plugging in a sine of theta. That's going to be a squared times 1 minus sine squared, and that 1 minus sine squared allows us to use an identity. If x equals a sine of theta, and I know that my a is 5, this is going to be that x equals 5 sine of theta. So let me go ahead and clean this up so that I can fit it all in this page. So knowing that x equals 5 sine of theta, remember part of our bookkeeping was figuring out that dx. So my dx is going to be the derivative of 5 sine of theta, which is 5 cosine of theta, and that's my d theta. So this dx, I'm plugging in 5 cosine of theta d theta for dx, whereas all my x's in my problem, I'm plugging in 5 sine of theta. But before we do that, let's continue on with our bookkeeping. Now the next thing I like to do after I identify the substitution I'm making is I like to set up the triangle. So if this is theta, my substitution that I'm going to make is that x equals 5 sine of theta. That means that x over 5 equals sine of theta. Sine is opposite over hypotenuse. So x over 5, opposite over hypotenuse. Here's my opposite side of x. There's my hypotenuse of 5. Here's the square root of 5 squared, which was 25 minus x squared. So you can see, just to double check, that is indeed my a squared minus x squared, 25 minus x squared. So I've set up the triangle. I'll be able to come back and use that as necessary. Now here's the optional step that I like to do outside of my problem. I know that 25 minus x squared, my a squared minus x squared, is going to simplify down into a product. I'm going to do that outside of my problem so that I can just plug that on in when I go to integrate. So if I know that a squared minus x squared is that 25, or let's write it as 5 squared minus x squared, I'm using that x equals 5 sine of theta, so I'm going to have 5 squared minus 5 sine of theta squared. So then I'll have 5 squared minus, bringing that exponent in, 5 squared sine squared of theta. Pulling out that 5 squareds from both terms, I get 5 squared times 1 minus sine squared theta. And there's my identity that I can use. Cosine squared theta plus sine squared theta equals 1, so 1 minus sine squared theta equals cosine squared theta. So this is going to be equal to 5 squared times cosine squared of theta. So for my bookkeeping, I have what 5 squared minus x squared is equal to when I make that substitution in terms of x. It's going to be 5 squared cosine squared theta. So now that I've finished my bookkeeping, let's go ahead and plug in everything I know. So I'm going to be integrating x squared, plugging 5 sine of theta in for x, is going to be 5 sine of theta squared. And then multiplying that numerator by dx, my dx is 5 cosine of theta d theta. So this is all times by 5 cosine of theta d theta. There's my dx. So I've taken care of my numerator. Now my denominator is the square root of 25 minus x squared. So I have the square root of, remember that bookkeeping that we did, that 25 minus x squared simplified down to 5 squared times cosine squared theta. So you can see by simplifying that down using that identity, we can now apply this square root to each of my terms. So let's go ahead and simplify down in our next step. So here we have the integral of 5 sine of theta, that quantity squared, is going to be 25 sine squared theta times 5 cosine of theta d theta. There's my numerator, all over my denominator, which, applying that square root, the square root of 5 squared is 5, and the square root of cosine squared is cosine. So I'm going to have 5 times cosine of theta in my denominator. So what do you see? Well, I have a 5 cosine of theta in my numerator and a 5 cosine of theta in my denominator. Those will cancel out. So all I have to integrate is, I'll pull that constant of 25 out in front, 25 times the integral of sine squared theta d theta. This is a lot simpler than what we started with. Look at that original in terms of x. That we didn't know how to integrate, but sine squared theta is something we easily know how to integrate. And just as I said at the end of that last example video, lots of times these trig substitutions will turn into trig integrals. So if we have sine raised to an even power, what do we have to use? We have to use the half angle identity. So 25 sine squared theta d theta, I'm going to use the fact that sine squared theta equals, I put the formulas up above, sine squared theta equals 1 minus cosine of 2 theta all over 2. So I'm going to have that 25 times the integral of 1 minus cosine of 2 theta all over 2 d theta. With this, I can pull a 1/2 out in front so that I have 25 over 2 times the integral of 1 minus cosine of 2 theta d theta. Now I can just integrate this. Integrating 1 will give me theta, so I'll have 25 over 2 times theta minus 25 over 2 times, well, integrating cosine, that's sine, but I have 2 theta, so I'm going to need to do sine of 2 theta all over 2. So I'm going to put 25 over 4 times sine of 2 theta. And this is an indefinite integral, so we're not going to forget our plus c. So I have 25 over 2 times theta minus 25 over 4 sine of 2 theta plus c. And just to make a quick note, if you were confused on how to integrate this sine squared theta by using the half angle identity, please refer back to that previous example worksheet where I went fairly in depth in working through these different trig integrals. Let's think back to our steps. What all have we done so far? Well, we identified the correct type of substitution needed and completed the necessary bookkeeping. We changed the original integral in terms of theta, including that dx. We simplified and integrated. This is the part we can't forget. We now need to go back to our original variable, which in this case is x, and we're going to use the triangle when necessary. So if we're looking at 25 over 2 theta minus 25 over 4 sine of 2 theta plus c, well, I don't need to go back to the triangle for this one because theta is some unknown angle. I don't know exactly what theta is, but I can solve for theta using my relationship. If x equals 5 sine of theta, that means that theta is going to equal the inverse sine of x over 5. You can see if I divide both sides by 5, I'll get x over 5 equals sine of theta, and then taking the inverse sine will allow me to solve for theta. So I'll have 25 over 2 times the inverse sine of x over 5. Now think about this, however. I have right here a trig function. I don't want the sine of 2 times the inverse sine of theta. I don't want some trig function nested in with another inverse trig function. That's just messy math. So what we're going to do is we're going to go back to the triangle to solve for sine of 2 theta. However, in this case, what is sine of 2 theta? Well, if we had just sine of theta, that would be x over 5. But the sine of 2 theta, we don't just multiply that by 2. We're going to use one of the formulas from up above to help us figure out what sine of 2 theta is. Sine of 2 theta, we'll use a double angle identity. Sine of 2 theta equals 2 times sine of theta cosine theta. So what I'll have here, zooming back in, I'm going to make a note that sine of 2 theta, and I'll go ahead and do this in yellow, using that double angle identity, sine of 2 theta equals 2 sine of theta cosine of theta. So if I plug 2 sine of theta cosine theta in, I get 25 over 2, because I'll cancel out a 2 from my denominator, so that'll be 25 over 2 times sine of theta cosine of theta. These are simple trigs, so I'll go back to my triangle. What's sine of theta? Sine of theta opposite over hypotenuse x over 5. So for sine of theta, I'm plugging in x over 5. And then what's cosine of theta? Well, going back to our triangle, we know what theta is, and cosine is going to be adjacent over hypotenuse. So I have the square root of 25 minus x squared all over 5. Now you see that when I set 2 sine of theta cosine of theta, when I plug that in for sine of 2 theta, I got 25 over 2 sine of theta, x over 5, cosine of theta, square root of 25 minus x squared over 5. And I can't forget, I still have that plus c. So now we have everything back in terms of x. However, this isn't exactly simplified because if you notice, 5 times 5 in that denominator will give me 25, which will cancel out with the 25 in my numerator. So completely simplifying, I'll get 25 over 2 inverse sine of x over 5 minus, that 25 cancels out, this will be x times the square root of 25 minus x squared all over 2 plus c. And that's my solution for example 1. So just a note, how do you know when to go back to the triangle? I mentioned that we don't want nested trig functions. So because theta is all by itself and I don't have a trig function of theta, I will just plug in the fact that theta is the inverse sine of x over 5. However, if I tried to do that for the second step, then I would have 25 over 4 sine of 2 times the inverse sine of x over 5. There is that nesting of my trig functions, which this is a lot messier than what it simplifies down to in terms of x. So when you have a trig function of theta, that's when you want to go back to the triangle. Let's go ahead and move on to one more practice problem. So for number 2, we have dx over x squared minus 4 to the 3/2. What is that sum or difference we're looking at? We're looking at an x squared minus an a squared. When we have x squared minus a squared, what substitution do we need? Well, this is part of step 1, identifying that proper substitution. And that substitution is going to be that x equals a secant of theta. So knowing that, if we have x equals a secant of theta, well, a in this case is going to be 2 because 2 squared gives us 4. That second part of step 1 is completing the necessary bookkeeping. So I'm going to do my x dx, then I'm going to create my triangle, and then after that, just to make my life a little bit easier, I'm going to figure out what x squared minus a squared simplifies down to. That way, I can just go ahead and plug that in. So x is equal to a secant of theta, where a is 2. So x equals 2 secant of theta. Next, dx, that's going to be 2 secant of theta tangent of theta d theta. That's taking the derivative of 2 secant of theta. Now I'll set up my triangle. So here's theta, and I have the x equals 2 secant of theta. That means that x over 2 equals secant of theta. But remember, what is secant of theta? That's 1 over cosine of theta. So if I have 1 over cosine of theta equals x over 2, that means that 2 over x equals cosine of theta over 1, which is just cosine of theta. That's telling me for cosine, adjacent over hypotenuse, my adjacent side to theta is 2, and my hypotenuse is x. So here I'll have 2, my hypotenuse is x. That means this unknown side is going to be the square root of my hypotenuse squared, x squared, minus 2 squared, which we know that 2 squared is that 4. So there is my x squared minus a squared. So we did indeed choose that right trig function to substitute in. So x dx done, triangle done. Now let's go ahead and figure out that x squared minus a squared to make integrating easier. So x squared minus a squared, when I plug in what x is equal to, that's my a secant of theta. So if I have x squared minus 2 squared, that's my x squared minus a squared, that's going to be 2 secant of theta squared minus 2 squared. Distributing that exponent in, that's going to be 2 squared secant squared of theta minus 2 squared. From here, we know that 2 squared can be pulled out. So I have 2 squared times secant squared of theta minus 1. There is that nice identity, secant squared theta minus 1, that equals tangent squared theta. So this is really 2 squared times tangent squared theta. So now that I've done all my necessary bookkeeping, let's go ahead and move on to step 2. So step 2, scrolling back up so you can see, is all about changing the original integral to be in terms of theta. Note, don't forget that dx as well. So let's go ahead and do that now. So we're going to change that original integral. Dx is the only thing in our numerator, so that was 2 secant theta tangent theta d theta. And in our denominator, well, when I go to plug x in, I only have x within that x squared minus a squared, so I'm going to be plugging in 2 squared tangent squared theta. So this is going to be 2 squared tangent squared theta. That is my x squared minus 4, all raised to the 3/2. And if you didn't do this optional step within your bookkeeping, that's okay. You're going to get the same result when you plug in x as 2 secant of theta. You're just going to have to simplify through your problem to get that 2 squared tangent squared theta. But doing this optional step, I took care of that already when I plugged my 2 secant of theta in on the side. I already simplified that down, so I can plug in that simplified version, that product. Now that I have this, let's go ahead and simplify. So our integral 2 secant theta tangent theta d theta all over 2 squared tangent squared theta all raised to the 3/2. When I bring that exponent of 3/2 in, it's going to cancel out with my squared. So I'm going to have 2 cubed, which is 8, and then I'm going to have tangent cubed theta. Again, that was me distributing that 3/2 to both 2 squared and tangent squared theta. Now from here, I can bring this 2/8 out in front. I will write it as 1/4, simplifying that fraction down. Secant theta will remain in my numerator, and in my denominator, I'll be able to cancel out that tangent of theta in my numerator, and one of my tangent of theta is in my denominator, so I'll have secant of theta over tangent squared theta d theta. So here is more of a simplified version of that integral. However, currently I'm not quite sure how to integrate this. So if I think back to my trig integrals, if I set my u as tangent, well, the derivative of tangent is secant squared, which I don't have in my numerator, so I don't have that good du. So what I'm going to do is I'm going to have to do a little bit of rewriting. I know that secant of theta is 1 over cosine of theta. So rewriting this, I'll get 1/4 times secant of theta is 1 over cosine of theta. Now, if I'm dividing by tangent squared theta, I know that tangent squared theta is going to be sine squared over cosine squared. But if I'm dividing by sine squared over cosine squared, that's the same as multiplying by cosine squared theta over sine squared theta. So this is my secant of theta over tangent squared theta. I just rewrote that fraction as multiplying by its reciprocal. So now you can see I'm actually going to get some stuff to start canceling out and simplify down even more. So I'll have 1/4 times the integral of my cosine of theta in my denominator cancels out with one of my cosines in my numerator to leave me with cosine of theta over sine squared theta d theta. So in this case, we had to do a little bit of algebraic or trigonometric manipulation in order to simplify this problem down. Now I have a good u substitution because the derivative of sine of theta is cosine of theta. So if I set my u as sine of theta, then my du is that cosine of theta d theta. So let's go ahead and make this substitution. So I'll have 1/4, and this will be du all over u squared. My u is sine of theta, so 1 over u squared du. Integrating this, I'll get 1/4 times the integral of u to the -2 will be u to the -1 divided by a -1, so this will be -1/4 u to the -1st. And don't forget that plus c. So I started with x's, I used thetas to simplify my integral, but then from there I actually had to go to u substitution in order to integrate. So I'm going to go back to theta and then finally back to x. So -1/4 u to the -1 plus c, I'm going to plug in what u is, which is sine of theta. So I'm going to write this as -1/4 sine of theta. All I did was bring this u into the denominator. And don't forget my plus c. Now this is the perfect case of going back to that triangle. Because I have a trig function of theta, I can use my triangle. If this was theta all by itself, we would just take that inverse secant in order to solve for theta. However, because this is a trig function, we don't want the sine of the inverse secant of x over a. We want to use that triangle. So looking at sine in our triangle, sine is opposite over hypotenuse. So we're going to have the square root of x squared minus 4 all over x. So this is -1/4 times the square root of x squared minus 4 all over x plus c. And one more thing just to simplify this down so I don't have a fraction within a fraction. Remember, dividing by a fraction is the same as multiplying by its reciprocal. So I really have -x over 4 times the square root of x squared minus 4 plus c. And that's my final solution on this example worksheet. Now I know trig substitution seems like a long process, so why do we bother with it? What's the point? Well, if you look at both the examples, we started out with integrals that we weren't able to integrate. We used that trig substitution to help us simplify that problem, and then we were actually able to integrate each of those problems. However, we just had that different variable, so we needed to go back to x in the end. And using that triangle helps us get a nice, clean, simplified answer that we'd be able to work with. And the instances where we wouldn't necessarily need to go back to that triangle would be like what happened in example 1 with that first term. We integrated and we get theta, but not some trig function of theta, just theta by itself. Or if we actually had a definite integral and bounds on these, we could switch the bounds in terms of theta and not have to worry about going back to x. But hopefully you found these problems challenging, but also a little bit fun. They're kind of like a puzzle, going back and forth between different variables to help simplify the problem. And we use that map of a triangle to help us get back when necessary. In the next example video, we're going to learn a new strategy of integration called partial fraction decomposition. So stay tuned, and until the next video, good luck with your online learning.